Look at example number 3. In this question, we're asked to find the acceleration due to gravity on the Earth, where the radius of the Earth is given and the mass of the Earth is given. And we also know the universal gravitation constant. So if you recall, in the earlier question we had solved in example number 2, we learned that the weight of an object could be calculated in two different ways. The force of gravity, which is the weight, can be calculated simply by taking the mass and multiplying by the acceleration due to gravity, which is really showing you that it depends on the acceleration due to gravity at that location. So if you have a greater acceleration, you have a greater weight. Or alternatively, you could calculate the weight by using Newton's universal gravitational law, which is g, that's the universal gravitation constant, times the mass of the object, times the mass of the planet that's on, which would be the Earth, divided by the distance between that object and the center of the Earth. So that would be the radius of the Earth, in this case, squared. Now, since those are both the same, we can set those two equations equal to each other. So we can essentially say mg is equal to gm, mass of the Earth, divided by the radius of the Earth squared. And you can see that the mass of the object cancels out, which means that the acceleration due to gravity, which is g, the universal gravitation constant, times the mass of the Earth, all over the radius of the Earth squared, is independent of the mass of the object. So now we could calculate what the acceleration due to gravity would be on this spherically symmetric mass. We're making that assumption for the Earth. So let's go ahead and substitute in here. We have for universal gravitation constant 6.67 times 10 to the power negative 11 Newton meters squared over kilogram squared, times the mass of the Earth, which is 5.97 times 10 to the power of 24 kilograms. I actually wrote not 5.98. I believe it's actually 5.97 actually. Divided by the radius of the Earth, which is 6.38 times 10 to the power of 6 meters. Now this is in kilometers here, but you would need to change that to meters because you have to, if you look at the constant over here, this is in meters over here. Okay, so go ahead and put that, by the way, this is squared, put that in your calculator now. You get an amount of 9.78 meters per second squared, which is a bit low. Now, if I had changed that, I guess, to 8, then our answer would be 9.80 meters per second squared. A quick note, by the way. So imagine here is the Earth here, right? And we are looking at a spot right here where this is obviously exaggerated, you're not that big, but this is the radius of the Earth here, your mass, and then the mass of the Earth. And if you were to plot, say, the acceleration due to gravity as r gets bigger and bigger, so let's take a look at what g would be on the surface of the Earth. So at this location right here with the radius r is equal to the radius of your Earth, your value right here is about 9.8. And then as you move further and further away, r gets bigger, the denominator, and so this graph looks like an inverse square graph, where the gravitational acceleration due to gravity, or your weight, is inversely proportional to the distance squared. Okay, that's it for example 3.